All right, welcome back, class, to week 2 of Chem220b. Last week, we began our discussion on linear response theory. We took some baby steps in first considering systems whose response is always linear, which we could demonstrate through exact calculation, namely harmonic systems or systems which exhibit Gaussian statistics. And we motivated from the central limit theorem why we might expect that generally systems are locally harmonic or obey local Gaussian statistics for fluctuations near enough to the mean. The central limit theorem provides some basic constraints, which, if satisfied, will result in random variables exhibiting Gaussian fluctuations. So today we're going to take 2 steps away from those simple cases. We're going to consider the response of a non-linear system to a small perturbation. Then we will consider a higher dimensional system and how it responds, building up complexity kind of step by step until at the end of this lecture, we'll have all the ingredients necessary, with a bit of an aside on the structure of multidimensional response, to actually write down an effective theory for density fluctuations for a liquid. So that's where we're going. Let's go ahead and begin. So let's begin with linear response in non-linear systems. And let's consider a simple, concrete nonlinear system. A system for which there's a one-dimensional potential, U of x, and dynamics evolve along that potential. Let's give a specific form to U of x. It will, at 0th order, or at lowest order, be locally harmonic about x, and locally quadratic about x. With alpha being a strictly positive number, this will ensure that the potential is bounded. So there are stable states for which the evolution can evolve. But unlike the simple harmonic oscillator we've considered up to this point, let's add in nonlinear terms of the form of higher order polynomials. Say the cubic term with some coefficient b and a quadratic term with some coefficient c. If we were to plot an example of what this potential might look like, around x is equal to 0, for small x, we should expect that the quadratic term dominates, so we will have something locally harmonic. Those nonlinear terms can then cause deviations, like so. We are imagining that the potential is stable. Such that the potential increases as x, ultimately as x gets much larger or smaller than 0. Such that it would support bound states, for example. So that's the system. If you wanted something a little more concrete, imagine you have a little particle that moves around in that potential. Now let's ask the question, what happens under a small applied constant force. Let's call it little f, such that now the potential consists of a sum of the original potential minus f times x. So what's going to happen? So we should expect, for example, that the average position of our little blue particle evolving in this potential will change. And let's try to understand concretely and quantitatively, in the limit that f is small, what is that change? What is the response of this particle in terms of its average position under the applied force? So as before, we can write an expression for the partition function for this system in the presence of that force. Let's give it the name Q of F. As usual, if there is only one dynamical degree of freedom, in this case, the position of the particle, again, we're working in a classical limit where we don't have to worry about what the conjugate momentum is doing. That partition function will be given just by an integral over where the particle can be and a Boltzmann weight associated with the original potential and one associated with this constant applied force. Now let's do the same trick we did with the harmonic oscillator. Let's multiply by 1 in such a way that we multiply top and bottom by the partition function, Q, in the absence of the force. As before, we can observe that everything in the highlighted part of the equation is the probability of observing the particle at position x in the reference system, in the system without the applied force. Integrating over all positions, the exponential of beta fx times the probability of x gives us an expectation value. In this case, as before, we've found that the partition function in the presence of the force is equal to that in its absence times an expectation value, e to the beta f, evaluated in the absence. So again, it is important to stress that this simple looking relationship encodes something really deep and interesting, that a system's fluctuations in the absence of a perturbation encodes what happens in the presence of that perturbation. That sort of statistical statement can be made thermodynamic by observing that a ratio of partition functions, Qf to Q0, is equal to a ratio or a difference of free energies, in this case the Helmholtz free energy in the presence or absence of the force. A change in a Helmholtz free energy under constant temperature conditions is equal to a reversible work. In this case, it's the reversible work to turn on that force, to apply the force to our particle. And we have an explicit expression in this average. So again, one of the phenomenal things about statistical mechanics is that it, in equilibrium, provides relationships between statistical objects, fluctuations, probabilities, and mechanical objects, the work to do a transformation. Okay, now, unlike the harmonic oscillator, we can't evaluate this expectation value. All right, so in some sense that's a bummer. Life would sure be great if we could evaluate any partition function we want. Nevertheless, the relationship we've arrived at still encodes useful information. So specifically, we've already observed that the log of Q of F is a cumulant generating function. That's a lesson we learned in introductory statistical mechanics, usually made fairly specific. The canonical partition function is in general a cumulant generating function, or its log is a cumulant generating function for the energy. In this case, we have a cumulant generating function which reports on the statistics of the particle's position. I.e., if we were to take a derivative of log of Q of F with respect to beta F at fixed beta, we would be able to compute the average of X in the presence of F. If we were to take a second derivative, we would be able to evaluate the variance of the position. And that structure holds to the nth degree. The nth derivative generates the nth cumulant. And in a general nonlinear system, there will be all cumulants present. Now, while we can't evaluate these cumulants directly, because to do so would be to evaluate this expectation value exactly, we can nevertheless ask for its behavior provided F is small. So we don't look too far away from a reference system for which we imagine we have lots of information. So specifically, if F is small, more on what small means in a second, we can Taylor expand the partition function, and specifically its log. And what would we get? Taylor expanding Q of F. Well, to 0th order, it's just Q of 0. To first order, we would get beta F the first derivative of the log of Q of F with respect to beta F, evaluated at 0 from our expression up here. The first derivative is just the average, evaluated at 0 is then just the average in the system without the force. Similarly, at second order, we would get a second derivative of the log of the partition function evaluated at 0, which would report on the variance in the absence of the force. Third order, you guessed it, will be dependent on the third cumulant evaluated in the absence of the force, and we could continue if we really, really wanted to. Now, taking the derivative of the left-hand side with respect to beta F, we have already identified that as the average position in the presence of the force. If we take the derivative of the right-hand side of its approximate form, given F is small, we would find the 0th order term does not depend on F, so taking its derivative, that term goes away. The second term, beta F average X at 0, says that the average position of X in the presence of F at 0th order is just what its average was in the absence of F. That's not super exciting, so let's go to one more order. The derivative of the second term, or the term that goes like F squared, would give us something that looks like beta F fluctuations of X in the absence of the force, and that would be good up to order F squared. So rearranging, we find that the average of X in the presence of the force less its value in the absence, so the change in the average position is equal to beta F, the fluctuations of X in the absence of the force, as long as F is small. So again, the change in the position after I apply a small force is linear in that force with a slope set by beta times the fluctuations of X in the absence of that force. So the fluctuations of X encode the response or the change of the average value of X when I apply a force. And now we understand what small must mean. Small must mean, so the domain of validity of this linear response is where we can neglect that higher order term that depends on the third cumulant. So if that third cumulant is large, reflecting very non-Gaussian statistics, we will only be able to use this linear response relationship for very small values of F. Note, in addition, that we don't necessarily know what that average or what the variance of X is in the absence of the force. It is not necessarily alpha over beta. We can only evaluate the variance in the absence of the force for a harmonic system analytically. So the game we're playing essentially is assuming that the reference system is something that we can independently interrogate, that we know something about it. We could simulate it or measure it. And now we're asking, provided we have those statistics, what can we use them for? And in this case, we found that knowing the variance in the absence of force tells us how the force would change the average position. In this case, a simple form for the variance would only be true if all of those nonlinear terms in the potential were 0. Okay, so that shows us that this structure of linear response that we worked out exactly for a harmonic system still holds, but it's an approximation in a general nonlinear system. And we've now understood exactly how good that approximation should be. It's good to order f squared, where that coefficient, the remainder term, has to do with the scale set by the deviations of Gaussian statistics. Okay, so now let's take one more step in generalization. Because there's a useful lesson here. So let's consider a system that's not evolving just in one spatial dimension, but let's take a baby step and ask what happens if we evolve in 2 spatial dimensions, such that there is some potential u of x and y, which has some general nonlinear form in both x and y, that we can decompose as a reference potential, something we imagine we have access to its information. And now let's ask for the response of this system to some constant force along just the y direction. Now, it's an interesting, one could take a step back and ask, what should we expect? If we push in the y direction, should the average of x change? Or under what conditions will the average of x change? So what do you think? Take a moment to take a guess. If we have a high dimensional system and we push along just one of those dimensions, these are Cartesian coordinates, x and y are in a geometric sense orthogonal to each other. Does that imply that their statistics are independent? That if we push on one, we don't affect a change in the other? So we can compute the average of x in the presence of that force. By noting that it is evaluatable as a specific expectation value. That will have some form of an integral over x. What is the Boltzmann weight? Well, it's some e to the minus beta, the bare potential, which exists in x and y, e to the beta fy. Now, unless that potential is separable in some simple way, such that u of x and y is equal to u of x plus u of y, I won't be able to factorize out that potential, and so I'll need to integrate over all y as well. X is what we're taking the expectation value with respect to, and I need to normalize this probability. Essentially, the partition function in this system is written like so. All right, looks a little more complicated than what we had before. Now let's imagine that f is small. If f is small, e to the beta f times y, if everything in that argument is small, then I can Taylor expand the exponential. E to the x for small x is 1 plus x. I know how to Taylor expand it, so let's carry that out. So approximately the expectation value of f of x in the presence of f. Everything lies under these two integrals. I have an x. I have a 1 plus beta f y to first order in f times the Boltzmann weight in the absence of f. Now note f appears in the numerator and denominator up here. So I need to Taylor expand that exponential in the denominator. Like so. I could write this now as in the numerator, if I multiply by the partition function in the absence of f, top and bottom, in this case, given by a double integral over x and y weighted by e to the minus beta u of x and y. That gives me a ratio of expectation values, again, because we have this and this being the averaging operation for the numerator and this and that being the averaging operation in the denominator. So I have a fraction or a ratio, x times 1 plus beta f y averaged in the reference ensemble. But I have another expectation value down below, which is 1 plus beta fy, all to first order in f. However, this is not exactly first order to f. It's not linear in f due to the presence of that denominator, so I should expand that denominator to be consistent with the assumption that f is small. 1 over 1 plus a small number is 1 minus that small number. So I get x times 1 plus beta fy averaged. I then have 1 minus, so 1 over 1 plus a small number is 1 minus a small number, beta fy in the reference ensemble, and this is now really good up to, let's not do that quite yet. So I can then, it expands that product. The first order term will have an x times the 1. That's just average of x in the reference ensemble. I then get a cross term with a minus x averages with 1. I get an x times, and move these averaging operations inside. I get a beta f average of y. I get a different cross term. It looks like average of, I get a, if I factor that term, I get a plus x times beta fy, all in the same averaging bracket. And now this is good up to f squared. Simplifying this, I find that average of x in the presence of f is equal to average of x in its absence. This beta f is common. And now look at this. This term here is the average. It's x times y averaged. This is x averaged times y averaged. That then is the covariance, delta x times delta y, averaged in that reference ensemble. And this is good up to order f squared. So what have we just found? We found that even if we push in the y direction, we will in general expect the average value of x to change. And we now know exactly the conditions over which that will happen and what its strength will be. It is dependent on how well x and y are correlated statistically. If x and y were uncorrelated, this factor here would factorize. I would average a fluctuation in x times a fluctuation y. By definition, that is 0. So to the extent that they are correlated, I will generate, through application of a force, a change in x. Now that change, the slope for which f causes a change in x, depends not only on whether f is positive or negative, but what the correlation is like between x and y. If x and y are anti-correlated variables, if I add a positive x, I will get a decrease. A positive f, I will get a decrease in x. If x and y are positively correlated, if I push on y and increase its value, I will also increase the value of x. Y drags along x as it's being manipulated through its statistical correlations. It doesn't necessarily have to be the case that there is a term in the potential. Well, in this case there is, because there's only one dimension. But in general, what one cares about is only how these two variables are correlated, not necessarily just that they will directly interact. Okay, so that's multivariate response. We're now in a position to actually begin to sketch out the theory for density fluctuations. Okay. So we're going to start first by imagining a fluid. Here's my fluid. There's a little region of my fluid. And envisioning that I can grid up that fluid into discrete cells. This will allow us to formulate things in vector spaces. And at the end of the lecture, we'll generalize this to a continuum. So we'll actually go off lattice, but let's start in the secure notions of a lattice system. So let's imagine each cell has some volume. And that there are m of them. And if I look at one of those cells, there is, in general, a density. I can imagine that the blue is just me squinting at molecular positions. I could ask, as we did before, how many particles happen to be inside that cell. If I know their volume and I know their number, I therefore know their density. And as particles diffuse and fluctuate over the course of thermal fluctuations, that density will change. Instantaneously, the density at cell Ri, I can write as some mean value plus some fluctuation. Because this is a fluid and therefore translationally invariant, the average density in one of those cells is just the bulk density. Each cell is statistically identical. However, if the density fluctuates because particles move in and out of those little cells, we are in no position, if we're considering a dense fluid, to assume that those cells are uncorrelated. In fact, we very much expect them to be very correlated. Let's define a correlation function for the fluctuations that encode how the fluctuations in the density of one cell depend on the fluctuations in the density at another cell. Specifically, we could ask, how do the fluctuations in density at cell I depend on the fluctuations in density at cell J? And let's give that variable the name chi. Now, if all cells are equal and we have translational invariance, it shouldn't matter which particular cells I pick. The labeling shouldn't matter. Similarly, it shouldn't matter whether or not I relative to J is to its left or to its right. Thus, this chi ij should depend on Ri and Rj in a specific way. It should only depend on how far apart those two cells are. for notation for the next couple minutes, let's call this then chi ij, and remember that it just depends on the distance between cell I and cell j. At any given time, the state of the system is given by a set of these density variables evaluated for each one of the M cells. Okay, so that's the setup. We're looking at a fluid. We've carved out a lattice with some specific volume, and within that lattice, the density will fluctuate. We're encoding or defining those fluctuations as a deviation from a bulk density. We've acknowledged that while the bulk density is a simple number, those cells do not fluctuate independently. And at a minimum, we'll have some covariance, some correlation function that tells me how one cell depends on another. Now, a bit of a leap of faith. Let's now assume that that set of densities that each fluctuation in density at each cell is a Gaussian random variable. They are not independent at each cell. There is a covariance that correlates two cells. Nevertheless, I can completely describe the fluctuations in all of these densities by just knowing its mean and that covariance. If that is true, which we have demonstrated empirically and motivated formally through the central limit theorem, we can write down an effective Hamiltonian, an effective prescription for density fluctuations of the form that is bilinear in the fluctuations of the density. So an effective Hamiltonian, an effective energy function that dictates the statistics of the density would look like fluctuation in cell 1 or in cell I times a fluctuation in cell J. If this looks like, this should look like a harmonic oscillator, so there is some effective stiffness. And that stiffness is the matrix chi ij to the -1. It enters through the definition of the correlation function. We remember for a harmonic oscillator that the variance of a harmonic variable enters in the denominator, not as the spring constant, but as the spring constant's inverse, the little alpha we've introduced a couple times already. Now this is a little more complicated because this is a matrix of inverse spring constants, which encode the correlations between these non-independent Gaussian random variables. Provided this is a good model for the fluid, we can ask questions like, how does a fluid respond to the application of a field that changes its density? So imagine we take our fluid, described by this Gaussian model, and apply a constant conjugate potential that might have some structure in space. Of this linear form. So it might depend on where in space it's being applied. So I give it subscript Ri. It acts conjugate to the density in that location of space. So this is a multivariate response. From the discussion we just had above, we know the fact that the underlying model is Gaussian means that the linear response for how the density at some point in space, call it Ri, will be changed in the presence of that field will be equal to beta sets the scale. This field acts not just on Ri, but on all of the cells. So if I push on cell J, for example, then how that perturbation at J propagates to I is through the correlation function, which tells me how well correlated cell J is to cell I. And now this needs to be summed over all J. J being just a dummy index, I could apply that potential to many different cells, and thus the response at a specific cell will be a sum over all the responses from the individual cells. This sort of thing we have not exactly proved. So in a very high dimensional case, if we have a linear combination of perturbations, but it is in your homework. So that's the response relationship. If we have some structured field moving our density around, the change in the density locally is given by a linear combination of the field times the correlation function where the scale of the fluctuations is measured with respect to kBt. So that correlation function that tells us how density fluctuations depend on each other, chi ij, enters in directly. So it's worth thinking a little bit about the structure. What should we expect chi ij to actually look like? Because of course that's going to be what dictates the response. Okay, so first, chi ij, there's two indices, so chi is a matrix. Which means that its inverse is not trivial to compute. Let's write down the matrix inverse of chi as two pieces. Some chi naught minus an inverse minus some delta chi inverse. Where chi naught inverse is the component along the diagonal of this chi matrix. So the ith jth element of chi naught inverse is equal to a delta function. So it exists only on the diagonal with some size, call it 1 over alpha I. This reflects self-correlations. Cell I has some fluctuations just due to fluctuations in cell I. So even if it wasn't connected to any other cell, the density could still fluctuate. And those self fluctuations have some scale we're calling alpha I. That means that delta chi is what encodes all of the correlations, the off-diagonal part. It encodes those intracell correlations. Now let's do a little bit of matrix algebra. We could simply write chi inverse by factoring out chi naught inverse. So we have a unit matrix less delta chi inverse times chi naught, which as a diagonal matrix inverts trivially, times chi naught inverse. And now we can take the inverse of chi inverse, getting chi. We have a component which transforms simply, the chi naught, because it's diagonal. Again, it transforms like a set of numbers. And now we have the identity matrix less chi naught inverse, chi naught, that whole matrix inverted. So the correlations, indeed, because they're not along the diagonal, don't transform so simply. If we wanted to compute them, we would need to construct that matrix of 1 minus delta chi inverse times chi naught and invert that whole matrix. Nevertheless, writing it like this lets us work out an explicit equation for chi, because we can write down an infinite order expansion for the right-hand side. Let's give myself a little room. So this is exactly equal to, so again, 1 minus a small number is 1 plus that small number plus that small number squared, etc. So to zeroth order, chi is equal to chi naught to second order I have a delta chi inverse chi naught plus a delta chi inverse chi naught delta chi inverse chi naught plus higher order terms. Multiplying out chi naught, I have chi naught plus chi naught delta chi inverse chi naught plus chi naught delta chi inverse chi naught delta chi inverse chi naught, blah, 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 blah. If we took the ijth element of chi, using the fact that chi naught is simple and equal to that delta function, we find the 0th order term is just alpha I delta ij plus alpha I delta chi ij alpha j plus, now the higher order term, we can use the delta function definition of chi naught sandwiched in the middle to write this as a sum over a new index n, alpha I delta chi inverse I n alpha n delta chi inverse n j alpha j, and so on. Now this structure looks like it's just adding complexity, but we see a bit of a pattern emerging. We get delta chi evaluated at some elements sandwiched with these little alphas. And those alphas, through their diagonal contribution, are simple. The next higher order term, you can even imagine leveraging that simplicity and working out that it would be a double sum over two additional indices, but the structure would be the same. There'd be an alpha delta chi inverse, an alpha delta chi inverse, an alpha, etc. In fact, because the notation becomes so cumbersome, it's useful actually to represent this series with a diagram. So let's introduce a diagram with an open circle that will be an index. In this case, call it I. A thick line for chi. So that would represent chi ij in its completeness, this term here. This expansion tells us that that's equal to alpha, evaluated at I, plus small link for delta chi inverse between I and j. That double sum takes an I small linker to an N that's being summed over. And connects that to a J. Instead of writing out the next order sum, we can present it graphically. It would look like I in another sum K to J. If we wanted to go even further, we'd have I to N summed over all N to K summed over all K, K to L summed over all L, now to J. And now look at the geometry that's coming out. We have this first order term, and then we just have a set of links that keep percolating out. And we know that if we sum over all of them, we get back the full chi between I and J. In fact, if I was to cut this link here, and ignore everything to the left, it looks like I have one node, one node goes to a next node. It looks like I have just repeated what I mean by chi in the simple expansion for chi. In terms of equations, if I replaced the expansion by reevaluating or acknowledging that because the sum keeps repeating its structure, if I looked at these terms, that's the same as that term, which means I could factor out all of those terms and it would look like just the expansion of chi again. I think it's a little easier to see it graphically that really this expansion of chi has a self-consistency to it. It looks like I plus an I to an M summed over, with that connected to J with a fat link, such that chi equals chi naught plus chi naught delta chi inverse chi. So again, up in the equation, if I have that self term plus a alpha delta chi inverse alpha, that looks like self term delta chi inverse self term. There's a self-consistency, which says that if I actually summed up all of those terms, I would know that a way of representing chi decomposed in the self term plus that single correlation function, that single correlator, some direct correlation between I and J, I get that total correlation back out. So this is a bit into the woods or into the weeds, but it says that multivariate response naturally admits a self-consistency. It also lets us understand how response develops. At linear order. And it does through all possible 2-point correlations. This delta chi ij inverse is what enters into the Hamiltonian of our model directly. We parameterize the interacting piece. The spring constant in our model is chi ij inverse plus the self term. If we subtract off the self term, that delta chi ij is a direct interaction prescribed in our effective energy function, in our effective Hamiltonian. Linear response, because it works on chi upright, not its inverse, says that the way the density responds is through, if we look at diagrammatically, a self piece plus all direct interactions, all delta chi ij between all possible pairs, I and j directly, I to n and n to j, I to n, n to k, k to j, etc. So that also tells you what's missing. Are interactions, direct interactions, that are more than pairwise in their nature. There is nowhere in this diagrammatic expansion where we see I and j and k interact all at the same time or all at the same point, coupled through a specific term in the Hamiltonian. Rather, I have a response on I from j mediated only by pairwise contributions. This sort of approximation is known as the random phase approximation. It is essentially what Debye and Huckel used in Debye-Huckel theory, something we'll work out explicitly in an upcoming lecture. And it's also related in the auspices of quantum field theory to something known as Wick's theorem. Okay, this is all on lattice, and we've delved into the structure on lattice. Now to the continuum limit. So on lattice, the state of the system was a vector where I ask for each component of the vector and it returns a density fluctuation in a cell. That vector, if I make the cells finer and finer, so the volume of those cells gets infinitely small, rather than having a discrete number of components to that vector, I will have a field or a function, delta rho of r, where r can take on any of an infinite number of values. Similarly, the Hamiltonian, in the absence of our field, which was a function of all of those components of the vector, written down as a bilinear sum as such. Well, in the limit that there's an infinite number of components, the discrete sum is going to become an integral. And the function on the vector space with discrete number of components becomes a functional of the function rho of r. And now I have two indices in the sum. So I have two field points, call them r and r prime, that I have to integrate over. And this correlator, that spring constant, now becomes a correlation function of the 2 points r and r prime. Now that matrix and its inverse were previously defined through a matrix inverse relation, namely if I sum over all components, chi I k inverse times chi kj. Definition of a matrix inverse is essentially this, that returns a Kronecker delta. The generalization of a now functional inverse is, as you might expect, through a Dirac delta function, where I integrate now, instead of sum, over all field points r double prime chi r double prime inverse times chi r double prime r prime. Its inverse, therefore, is a Dirac delta of r minus r prime. I can write now my perturbation to my original Hamiltonian. Now acting again on the field, the density field, where the density is a function of the points in space. The perturbation previously all the way back up here, some delta rho times some potential phi evaluated on the field points. That sum then becomes an integral phi r times delta rho of r. And now you might just be able to intuit the linear response relationship that would follow from this perturbation to the Hamiltonian. If I ask for what is the deviation in the density at position r in the presence of that field. That is going to be given by an integral over points r prime, all the places that some applied potential r prime can act, and mediated back to r through a correlation function, chi r minus r prime. Inserting what we mean by chi as the correlation function between density fluctuations at r and r prime. So we have here a generalization. Of course, this is evaluated in the absence of the perturbation, something we'll expand upon next lecture. We now have a way of talking about how the density field constructed from the fluctuating positions of particles in our solvent, if I apply a field, the response of the density locally in space is linear in the potential and mediated through a correlation function that tells me all the places that the potential acts and how that point in space is statistically correlated with the point in space, r in this case, whose response I'm asking for. So where this is going, and which you might expect, is this potential could actually be an intermolecular potential. The perturbation might be to take a solvent and grow in a solute, or name that solute to be, give that solute the properties, the interaction potential that is identical to the surrounding solvent, and thus I'm growing in a new solvent molecule. This then tells me how that the density correlations or density response is to that solute or solvent molecule in the dense solution. If the applied potential really is the interaction potential, this then will give me a means by which I can deduce the structuring of a fluid as that solute is placed in the solvent, or the native structure. If the solute is identical to the solvent, what is the native structure in the solvent? So we'll, in the next couple lectures, expand on that and expand on where these correlation functions would be deduced from. How do we know them? And that'll get us, what is their structure in this continuum space? That'll get us a bit into scattering theory, which is how we know what the structure of a fluid is. All right, that's where we're going. And that's all I got. So I look forward to seeing you all in small group discussions this week. Do come with questions. I'm looking forward to it. All right.